Hello friends, in this video I'd like to solve the following problem from the Romanian International Mathematical Olympiad Team Selection Test 1996, problem number 1. Let n be greater than or equal 3, let it be an integer, and let f from the set r squared into r be a function such that f of a0 plus f of a1 plus and so on plus f of a sub n minus 1 equals 0 for every regular n-gon a0, a1, and so on up to an minus 1. We wish to prove that f must be constantly equal to 0. It's a nice problem. It appeared on this Olympiad, but also it appeared few years later in simplified form as problem A1 on Putnam 2009. I will provide a link in the video description. And here are my hints for this problem. First, fix a regular n-gon with vertices a0, a1, and so on, and let akj, k in subscript, j in superscript, yes, be point ak rotated by angle 2 pi j over n about point 0, where jk go from 0 to n minus 1. So the idea is to fix a0 and to rotate every other point n times by angle 2 pi j over n. After n rotations, of course, we are where we started. And crucially, consider a0j, a1j, and so on. So with fixed upper index and lower index goes from 0 to n minus 1. What figure is this? And moreover, consider a subscript k rotated by 0 degrees, ak rotated by 2 pi over n, and so on. So say something about these figures. So give this problem a try, and I will see you in just a minute. Okay, so here is my solution. So as I suggested, let a0, a1, and so on, an minus 1, be a regular n-gon. A regular n-gon, okay. And let, as I suggested, akj be ak rotated by 2 pi j over n about point a0, where j and k, of course, go from 0 up to n minus 1. Okay, notice a few things. First thing to be noticed is that a0, 0 or a0 equals a0, 0 because it's this very point rotated by angle of 0. Well, a0 rotated by anything is still a0, so it's a01, a02, and so on, a0 and minus 1. So point a0 stays the same, but because we are rotating about a0, of course. Second observation is that a0, j, a1j, a2j, and so on, an minus 1j, well, it's a regular n-gon. It's a regular n-gon. Well, why is that? Well, since we are taking some regular n-gon and we are rotating its vertices by the same angle about the same point, we know that rotation about a point is isometry, so the image of a regular n-gon is still a regular n-gon because distances and angles are preserved. And moreover, a k0, a k1, a k2, a k n minus 1, well, what is it? It's also a regular n-gon. If k is greater than or equal 1, because for 0 we have we have degenerate n-gon, degenerated to 1 point. Okay, why is that? Well, it's because we are taking some point ak. We have somewhere here we have point a0 basically, and we are taking this point and we are rotating it n times about this point. So what appears is exactly a regular n-gon. Okay, good to know. And now I wish to consider the following double sum. First sum goes from, let's say, j equals 0 n minus 1. Second one goes from j equals 0, from k equals 0 to n minus 1. And we have ak subscript, aj superscript. Okay. Well, notice we have established that our inner sum is over k. K changes. And now we know that for every j, this is a regular n-gon. So our inner sum is 0. So our whole double sum is also 0. But notice that I can change the order of summation. So first I will sum over k from 0 to n minus 1, and then I will sum over j from j equals 0 to n minus 1. And now I wish to do one thing. I wish to split my sum. First sum will be with k equals 0. So j goes from 0 to n minus 1 and k equals 0. Very well. And my second sum will go from k equals 1, n minus 1, from j equals 0 to n minus 1. Now, what is it? Well, let's take a look. Here we are rotating point a0, and every rotation of a0 is a0. So we have n times a0, because we have n terms in our sum. N times f of a0. And what about the second sum? Well, let's go back by our second fact. For every k from 1 to n minus 1, this is also a regular n-gon. It's also a regular n-gon. So this inner sum, where j is changing, k stays the same, is also 0. So we have, to be honest, we have nothing. It's plus 0. And if you look closely, 0 equals n times f of a0, which means that, in fact, for every a0, f of a0 is 0, which means, because a0 was arbitrary, our function is constantly 0. And that closes our proof. Very nice problem. And one more thing before you go. I have made a drawing of this situation. Maybe I will make it slightly smaller. Okay, very well. Now, what is it? Well, this drawing visualizes my proof. First, notice that I have fixed some n-gon, this pink n-gon, a0, a10, a20, a30, a40. It's a regular pentagon in this case. I am taking every vertex and I am rotating it. So for example, a10 goes to a11, then it goes to a12, a13, a14. A regular pentagon is formed. Then I'm taking, for example, a20, I rotated it, a21, a22, a23, A24, another irregular pentagon is formed. Then I'm taking A30, A31, A32, A33, A34, yet another polygon. And finally, I'm taking A40, R41, R42, R43, R44. Yet another polygon is formed. So these 5 regular polygons, and A0 stays the same. So first I have 5 regular pentagons, and these 5 pentagons are represented by the first sum. Yes, k goes from 0 to n minus 1. If n equals 1, we have 5 polygons right here. And finally, after a bunch of rotations, if you look at these dashed lines which I drew, we have 4 regular n-gons. And that's this last sum, because k goes from 1 to n minus 1, and I am having regular n-gons, but only from 1 to n minus 1, so one less, 4 polygons. And A0 is counted n times in total. And yeah, that's it. It's a very, very nice problem, I'd say. Very creative. Somewhat unusual for our functional equation. Thank you for watching, and I will see you next time. Goodbye.